Hello everybody, welcome to section 5 of chapter 3. We're going to study a little bit further how vectors work, and we're going to talk about this idea of relativity, something we haven't really covered much quite yet for a couple of reasons. One is really to understand relativity, we have to understand motion first, and that's what we've been covering so far. Alright, so here we have our first example of relativity. When we say that a boat is trying to cross a river, the river is moving in a different direction than the boat is intending to move, and so the combination of the boat's movement and the river's current ends up making the boat appear to move on a diagonal instead of straight across. The person in the boat, though, experiences going straight across even though there is a diagonal to the motion. Okay? Same thing happens in an airplane. A plane doesn't necessarily see how wind impacts it as it's flying. In the pilot's mind and in the pilot's eye, he's flying straight, but wind actually blows him off his path. And we're actually going to use some of our concepts of total resultant vectors to solve some of these problems. What I want to make sure we understand is what we're talking about is relative motion. And so everything has a velocity in these situations that is relative to a medium. In one case, it's the river. In one case, it's the ground. A lot of times we can talk about the difference between the observer and a frame of reference of an observer versus, someone who's experiencing the motion versus someone who's watching the motion from far away. These are all just excuses to add velocities again. Nothing is different. We've already talked about the rules of vector addition. All of this is going to apply as it did before. What we're going to see is a lot of times instead of solving for a resultant vector, we may be solving for one of a component of two vectors instead of just the resultant. We have an example here in one-dimensional motion that says that if a hockey player is moving at 5 meters straight toward the goal and then drives the ball in the same direction with a velocity of 30 meters per second relative to her body, then the velocity of the ball is actually 35 meters per second from the goalkeeper. So the person who is moving at 5 meters per second adds 30 meters per second to the velocity as they hit the ball, whereas the goalkeeper who isn't moving sees the total motion as 35 meters per second. Okay. In 2 dimensions, we get a little bit more difficult, just as usual. We're going to use all of the equations that we've seen before. These guys are going to help us understand how when we're adding velocities, what we need to be able to do is we need to be able to break our components down into vectors so that we can add x's and y's, or if we can't break them down into components, maybe we can solve for, say, the final velocity of a resultant and the angle at which it's happening. I just want to remind you of the equations. Okay, and here we have our first problem, and this is that boat problem. And so what we're asked is, what is the total displacement of the boat relative to the shore? In other words, we want to know the angle and the total movement of the boat given the information we've given. Now, this seems like a pretty simple situation because the v of the boat also happens to look like our y vector, and the v of the river in this case, because they're kind of acting on on straight lines, and then v of the river looks exactly like vx, so it's the total x direction versus total y direction. In order to get the v total, since this is just adding components of vectors, first thing we can do is do the Pythagorean theorem. And then the other thing we can do is the inverse tangent to find the angle. Okay. Our lovely calculations. Usually you guys are doing this for me in class, and I'm doing it for you this time. When we're doing these calculations, please don't forget that your calculator needs to be in degree mode. I'm sure you miss being reminded every day. So I got my final velocity to be 1.42 meters per second, and then I need to figure out what my inverse tangent is of vy over vx, and vy is 0.75 divided by 1.2. I got 32 0.00 degrees. And this looks like that theta is positive, so it's above above the x-axis, so it's a positive value. And this is 1.42 meters per second. Okay, hopefully you feel pretty comfortable being able to do that one. That one was a pretty simple example. All right. Next one we're going to do is the wind problem. And so for this particular problem, you'll note that we have information for V total and for VP, but we do not have any information about VW. Okay. So our goal here is going to be to figure out what VW is. In order to do that, I want to remind you that V total is a resultant vector, okay? And a resultant vector, a resultant vector can be broken down into Rx and Ry. We can solve for that given the total information we've been given so far, because we know V total is 38 meters per second. And we know the angle is 20 degrees west of north, which you can see has already been converted for us to 110 degrees. So we can do that. What I'm going to do is I'm going to solve for the x and y components of this first. And I'm going to get the 38 times cosine of, in my case, I'm going to do the converted angle from 0, just because we've talked about convention. Why not? It'll give me x's and y's that are negative or positive according to where they're already located. I'm going to get an Rx that is negative and an Ry that should be positive 35.71 meters per second. Okay, I'm going to write some of this information off to the side. I want you to be able to track information. And Ry is 35.7 meters per second. Okay. All right, from here, I'm going to remind you that additionally, Rx should be equal to the sum of all of the x components. Same for Ry, should be equal to the sum of all the y components. Okay, now let's designate VW as B and then VP as A. Okay, just for consistency's sake, we need something to be A and something to be B. Now, VP is going due north. That's the actual velocity of the plane. VP only has a y velocity because it's heading due north. It only has y velocity, which means that its x velocity is 0 meters per second. Okay, and remember we said we were going to say that the plane was going to be the a vector. Okay, VW, which is B, we don't know anything about. So we don't know BX or BY. Okay, but we now know AY, AX, and RX and RY. So we can plug what we know into these equations for X and Y, and we can calculate the unknown components of BX and BY. So we're going to go ahead and we're going to do that. I'm going to rearrange both. BX is going to stay the negative 12.997, and then BY becomes 35.708 minus 45, which will equal negative 9.29 meters per second. Okay, so before we move on, here's my bx and my by. I have the x and y components for a vector that I had not had any information about. I want to know theta and I want to know b. I don't want to know x and y, I want to know b. Now, before we do anything, does this vector pointing downward have a negative bx and a negative by from where it's currently located? The answer is yes. So the fact that my things are negative so far is lending itself well to our particular, oops, this is why, sorry, is lending itself well so far. Like, right, like we're on track. Okay, so now let's do theta and v for our b vector, okay? So I'm gonna do b equals the square root of the x and y components added together, and I'm going to do theta is equal to inverse tangent of the y over the x Give me a second to do it in my calculator. Okay. I got b to be 15.98 meters per second. So the wind is blowing at a 15.98 meters per second speed. And then I got my tangent, my inverse tangent to be 35.55 degrees. Okay, so this angle is 35.55 degrees. And VW is 15.98 meters per second. Okay, all right, and that's, so again, all we're doing is we're manipulating the addition of two vectors. Now, when we say two vectors, we don't necessarily mean like an x and a y component. We mean that everything has x and y components, so don't forget that. All right. So just kind of classic, just kind of good wrap up here, just where this all comes from. We are going to focus everything that we've done so far, and we have already been doing this, we're just giving it a title. We call these things relative velocities because every velocity that we have manipulated thus far is relative to some kind of reference frame. And this idea of a reference frame is new for us, but the reason why we need to introduce it is because now we can look at reference frames from different observers. So now we can look at how the person on the plane feels compared to a person on the ground watching a plane. Those two different types of motion are relative in that it matters who is actually describing the motion or who is experiencing the motion. And this whole idea of relativity is something that has come along in the last 100 years of physics. And what we typically are going to study is classical relativity that was initially kind of described by Isaac Newton. We're actually moving towards Newton's laws of motion first, where relativity has actually been around for a really long time. It's something that Einstein has really talked a lot about in terms of modern theories. We're going to focus more on Newton's version of classical relativity because most of what we are dealing with is speeds below 3 million meters per second. Anything higher than that, and we're out of this world, literally, in terms of physics. And so just kind of give you an idea, here we have a situation where we've got someone on the shore, and his version of what happens on this boat. This person on the shore sees this. He sees this curve. But the person on the boat, so we're talking about like a pair of binoculars dropping, but the person on the boat, when they drop it, it drops straight down. The difference is the person on the boat is experiencing the motion under which the object he's riding is going through, and the person on the shore is not experiencing that same motion. So this is a good example of how this classic relativity is going to be applied in our situations. Okay, and just kind of a wrap up. Don't forget, we've talked a lot in this chapter about these different equations, and we've learned how to apply them in several scenarios. Next up is going to be some practice problems for you to start working on. Have a great day.